Hi, everyone, and welcome to our session. Today, we'll be talking about how customers use accelerated compute at Amazon to build and deploy models in generative AI. My name is Dwij Bajpai, and I'm a senior product manager at Amazon EC2.
I'm Samantha Pham, and I'm a principal product manager at EC2.
And hi, everyone. My name is Kirbani. I'm an AI engineering lead at Meta.
We have a lot to cover today. We'll first provide an overview of the different use cases we're seeing in generative AI across different industries, with a focus on the trends that we've observed over the past year. We'll then talk about certain key customer needs that have emerged in common across the customers in this space, and use this as a framework to talk about the capabilities that we're developing in EC2 to help customers train and inference their machine learning models. Next, we'll talk about what we call the generative AI stack, and how we're investing in every layer from the compute infrastructure to orchestration to managed services like SageMaker and Bedrock to make our accelerated compute more accessible to customers. And finally, we'll hear from our customers themselves. And we're really excited to have Kirbani with us today to tell us about the industry-leading AI research happening at Meta. Generative AI has touched pretty much every industry over the past couple of years. In healthcare, customers like Amgen are using transformer-based models to design proteins to accelerate drug discovery. It's been a revelation in the scientific community that the language of proteins and of our own biology can be learned by machine learning models, which can then generate candidates for new drugs and therapies. LLMs also have the promise to significantly reduce the administrative burden in the healthcare system by making it simpler to document and process electronic medical records. Certain companies are also fine-tuning their LLMs on their publications to make their research more accessible to scientists during the early stages of R&D. And we're still in the very early days for how healthcare will transform every aspect of how AI will transform every aspect of healthcare, from R&D to operations to manufacturing to healthcare delivery. In the industrial and automotive space, customers are integrating generative AI into robotics to create robots that can perceive the world around them and respond to events in real time. This can make robots more safe and efficient and improve the efficiency of manufacturing lines. Companies like Ferrari are using generative AI in their vehicle design to reimagine their customer experience so that customers can visualize highly realistic renderings of their vehicles in 3 dimensions before pushing the vehicles to production. In financial services, companies are fine-tuning LLMs on annual reports and financial statements to make their data more accessible to investors. And in retail, earlier this year, we announced a GenAI-powered assistant called Rufus for Amazon.com that you can interact with while you're shopping on the site. You can ask Rufus open-ended questions like, I'm interested in oil painting. What products should I purchase to get started? Rufus is also trained on the product catalog of Amazon.com and on customer reviews, making these a lot more accessible when you're trying to figure out what products to buy. And finally, in media and entertainment, companies like Adobe are creating multi-modal models that enable you to create cinematic experiences from a few lines of text. This is fundamentally changing the creative process, wherein creators can converse with intelligent models to rapidly create and iterate on images, short videos, and maybe in the not-too-distant future, even full-length feature films. And these are just a few examples of the many use cases we're seeing across industries, and it's continuing to evolve. And we at the compute layer in EC2 have an interesting vantage point into the industry for how these different trends are evolving. So let's talk about 3 trends that we've observed over the past year. The first trend is that LLM training is continuing to increase in scale. The biggest training jobs can leverage over 10,000 GPUs in one synchronous distributed workload. We're continuing to extend the scale of our clusters to support hundreds of thousands of accelerators, to support training of the next generation of foundational models on Amazon. At this scale, efficiency and reliability become crucial for us to focus on, as we'll talk more about later on. The other trend that we've seen this past year is that LLM inference has picked up significantly in various regions around the globe. Companies all around the world want to integrate the most powerful LLMs into their applications. It's really exciting to think that you could be in, let's say, a remote village in India and interact with the most powerful models in the industry in real time. And we are very focused on expanding our compute footprint and the economics of our compute to make this possible. And finally, if 2023 was the year of text-based LLMs, in 2024, companies are increasingly focused on multi-modal LLMs. It's really fascinating to see these models evolve into truly audiovisual entities with upstream layers dedicated towards decoding video and audio information, and downstream layers dedicated towards more abstract reasoning. Kirmani will talk more about this later as well. Deploying a model that can respond to audio and video in real time is introducing new requirements for our compute infrastructure. And we'll talk more about this later on. So these are high-level trends, but Samantha, it'd be great to learn more about the specific models and use cases that we're seeing trained on EC2 instances today.
Yeah. So like Devish mentioned, we're seeing a huge growth and emergence in the multimodal model space, but we're still seeing a lot of innovation in text-based LLMs where customers are building models of different sizes ranging from millions of parameters all the way up to trillions of parameters. These customers are varying their sizes of their models in order to help optimize and balance their performance and their costs, especially now that they're looking to start deploying them globally and figuring out how to get the right infrastructure to deploy their specific model types. Additionally, we're still seeing a lot of customers that are building out vision, speech, and recommender systems. These models tend to be much smaller than multimodal models and LLMs, but they have large data sets that need to be pre-processed in real time. That makes it extremely important for these customers to balance the right amount of CPU and GPU power on their instances. More and more, we're seeing customers in this space also start to adopt transformers, which allows them to better parallelize their workloads through self-attention. This starts to draw more of a common thread between all of the different types of model types we see customers building these days. And so moving on, we're starting to see another common flow between customers across different model types is their life cycle from inception of a model all the way to deployment. The first step we typically see customers start with is prototyping, where they're trying to test out new ways to optimize the performance or iterate on their model architecture. This tends to be the least compute-intensive stage of their life cycle, but it requires highly interactive hardware so that researchers can quickly test out new theories. Next, customers move to pre-training, where customers are training with clusters of up to thousands of accelerators. This makes it extremely important for customers to find the most optimal way for them to parallelize their workloads based on their model types. Additionally, it's extremely important for them to figure out how to optimize communication across different nodes within their 1,000 accelerator clusters. Next, we see customers moving to fine-tuning. Some customers will skip the prototyping and pre-training stages by using open-source pre-trained models from foundation model developers. But either way, when you're fine-tuning, you're typically looking to adapt these pre-trained models to fit your specific use case or your specific application. Customers will use new data to tweak the parameters and retrain the model for their specific use cases. There are two typical ways that we see customers do this. First, they do full fine-tuning, which means that they're updating the entire neural network of the pre-trained model. This can be an extremely compute and memory-intensive way to fine-tune. So customers that are looking to lower costs will potentially use parameter-efficient fine-tuning, where they're only going to update a small subset of their parameters or add an extra layer on top of the pre-trained model. This helps customers reduce the amount of compute and memory required to fine-tune, and therefore lowers their overall costs. Once customers are ready to deploy their models in production, we see them doing that in two ways. First is through real-time inference. This is where customers have to prioritize performance, where they're looking to optimize and lower latency as much as possible so that their end users have the best overall customer experience. The second way is through batch inference. This is where customers are able to optimize more for cost efficiencies, looking to lower all the overall costs per token generated. So now that we've talked about the life cycle of an AI journey, let's talk about common needs that customers see.
Yeah, so as we discussed, there's a real diversity of workloads that we see on our EC2 instances. But what are some of those things that customers consistently value over time? The first is performance. During training, higher performance means that you can accelerate your time to train, meaning that you can develop and iterate on your model and deploy it to production more quickly. During inference, higher performance means that you can inference bigger models at lower latency, meaning that you can create a more engaging experience in real time for your end users. Of course, as you start to scale your generative AI models from tens to hundreds to thousands or even millions of customers, managing your economics at scale becomes crucial. This is why we are always focused on delivering what we call higher price performance with each new EC2 instance, so that every dollar that you spend on training or inference gets you that much more performance with newer generations. The third key customer need is security, and actually this is the one that we take more seriously than anything else at Amazon. Your end users, when they're interacting with the model, may be sharing highly personal information, and they need to have the assurance that their interaction with the model is kept secure. If you invested significantly in developing a model, you need to make sure that your data and your model weights are kept secure as well. We'll talk more about how we deliver industry-leading security capabilities and features through the AWS Nitro system. And finally, ease of use. It can be complex to manage a fleet of thousands of instances to scale up and down your training workloads and your inference needs. And this is why we look at every layer of the stack, and we try to simplify what we call undifferentiated heavy lifting, so that customers can get the most out of our compute without having to piece together all the different pieces and invest in, let's say, highly specialized MLOps teams. So performance, cost, security, and ease of use. Let's use this as a framework to talk about the capabilities that we're developing in EC2 to help customers meet these goals. Maybe one way to make this more concrete is by asking the question, what would you see if you popped open the hood in one of our EC2 instances? At the heart of our accelerator compute instances is the accelerators themselves. We offer a range of accelerators from NVIDIA GPUs to silicon from our silicon partners like Intel, AMD, and Qualcomm, to our own custom-built AI accelerators, Trainium and Inferentia. Many of our accelerator compute instances also feature a highly performant chip-to-chip interconnect within the instance so that GPUs can talk to each other at high bandwidth and low latency. We'll talk about why this is important. Above the accelerator layer, you have certain instances have a PCIe switching layer that connect the GPUs directly to instance networking or local storage. Crucially, the data can get on and off the GPUs without having to go through the CPU, which can slow things down. And finally, you have the host layer that has the CPUs that actually host the instance that you launch an SSH into. And one of the main functions of the host layer is to ensure that your compute environment is kept secure at all times. But let's dive deeper into the accelerator layer and learn more about that.
We typically see customers use 3 different types of hardware for accelerating their AI/ML workloads, starting with CPUs. CPUs are often used for more highly serialized workloads, such as time series models or linear regression models. At AWS, we support customers that are using CPUs for their AI/ML workloads by offering a broad set of different types of CPUs, including AWS Graviton chips, as well as Intel and AMD CPUs. Eventually, as customers start to build more complex and larger models, they find that the performance offered by a CPU is no longer sufficient. And so that's when customers start to look at GPUs for their acceleration. GPUs allow customers to better parallelize the compute so that they can better optimize performance and costs. At AWS, we offer a broad set of different types of NVIDIA GPUs for customers to accelerate their AI/ML workloads. But these GPUs do tend to still be a somewhat general-purpose compute entity because they offer hardware optimizations for other types of workloads, including graphics renderings, video transcoding, or HPC workloads. And so that's where customers can further cost optimize and enhance their performance by using custom AI accelerators. These are purpose-built specifically for AI workloads, which means at a silicon level, designers are making architectural decisions that help optimize the performance for AI workloads specifically. We support a set of different types of AI accelerators, ranging from our custom-made AWS inference and Trainium chips, as well as AI accelerators from both Intel and Qualcomm. Next, we'll look at an example of a custom AI accelerator using our AWS Trainium chips. Just this morning, we announced the general availability of our TRN2 instances, which are powered by Trainium 2 chips. These accelerators are purpose-built to offer customers the best ML performance at lowest cost. They are built using neuron cores that are designed specifically with compute engines that enhance AI workloads, including tensor, vector, scalar, and general purpose single instruction multi-data engines. These instances also were built in order to take advantage of trends that we're seeing and address those for customer in the AI space. And this means what we're seeing is in terms of the model sizes growing larger, customers are more focused on making sure that the accelerators have enough memory to fit their models, and the memory bandwidth is fast enough to offer them the best performance. And so that's why the Trainium 2 accelerators are built with 96 gigabytes of memory per accelerator. And across a single server with 16 accelerators, you can get up to 1.5 terabytes of aggregated high bandwidth memory at 46 terabits per second of memory bandwidth. Additionally, we also iterated on the technology for our neuron link, and this enables customers to get up to 1.5 terabytes per second of interconnect across accelerators in a single instance to make sure that these models that are large and spanning multiple accelerators are optimized in terms of performance. So now that we've talked about the accelerator layer, let's move up into the architecture and talk about the components that we find in the switching layer.
Yeah, so let's talk more about the switching layer, and first we'll talk about networking, and then we'll cover storage. Our accelerated compute instances generally feature the highest instance networking of any instances in our portfolio. And we provision this much networking because we know that customers will scale their workloads out to hundreds or even thousands of instances. A few years ago, we took a step back at Amazon to ask the question, how do we design a network protocol that is efficient, reliable, and secure at scale? To meet these requirements, we designed the SRD protocol, which underpins the elastic fabric adapter, which is the networking interface in these instances. I'll talk about two features of SRD today. The first is adaptive multipath routing. SRD actually splits the packets across multiple routes within our networking fabric to get from one instance to another. And it actually measures the round-trip network latency for each of these paths and starts to reroute packets if it notices congestion in a certain area. Congestion can really slow your workloads down, and so this helps ensure that you see consistently high performance for your distributed workloads. The other feature is out-of-order packet processing. Traditional HPC protocols require packets to arrive in order. And if you drop a packet in the network, you actually have to retransmit a bunch of packets to recover from that. And this shows up in your P99 latency, because whenever you drop that occasional packet, it takes quite a while to retransmit all of the packets and recover from that. EFA can actually process packets out of order at the hardware level through the Nitro cards that process the packets. And so we can significantly improve that P99 latency, giving you more consistent performance at scale. But why is all of this important for machine learning workloads? So to give a quick background on why instance networking is so important here, let's look at an example. If you take a model like Llama 405B from Meta, if you use that model in the FP16 data type, you need two bytes in memory per parameter. So 405 times 2 is 810 gigabytes of memory. The most GPU-intensive GPUs have, the most memory-intensive GPUs have up to 140 gigabytes of memory per GPU, meaning that you can't fit that model on one GPU. You need to split it across multiple GPUs, and oftentimes across multiple instances as well. During training, you also usually split your data set across multiple GPUs as well. meaning that at any given point in time, a GPU in your cluster is working on one part of the model on one part of the data set. What this means is that at a regular cadence, the GPUs need to share information at high bandwidth and low latency so that they can synchronize gradients and each GPU can have an updated copy of the model to continue with training. This is why the bandwidth and the latency between GPUs becomes so critical to optimize. When we released P5 instances, we improved the completion times for collective communications by over 5x, improving the performance of distributed training at scale. Actually, yesterday we announced a new instance, P5EN, that further improves latency and completion times for common collectives. So we're continuing to innovate to push the boundary to help customers train at bigger and bigger scales more efficiently. One other thing we'll point out about our EFA instances is that they're generally deployed on EC2 Ultra clusters, which is a term we use to describe non-blocking networking infrastructure in our data centers. Non-blocking means that you can drive the peak instance networking on all of these instances at a sustained basis without oversubscribing the network, which is important in large-scale distributed workloads. We're continuing to push the scale of our Ultra clusters, and they'll support hundreds of thousands of accelerators for the next generation of training workloads. Ultra clusters also offer efficient access to storage like S3 and FSX. And actually, earlier this week, we announced that you can directly access FSX through EFA, giving you highly performant access to storage. But let's talk more about our storage options in general.
Customers have large amounts of data that they need to be able to access within their training clusters or with their production infrastructure that's deployed globally to support their end users. That makes it crucial for customers to figure out the most optimal way to store their data. And so AWS offers the most complete set of services for storage across different types of files, from objects to blocks to file systems. Seeing how customers use it in reality across their different types of ML workloads. We see customers using local instance storage for some of their temporary and checkpointing data. This is the storage option that's closest to your compute as it lives on the instance with your accelerators. They are using SSDs, which are ephemeral storage, because once your instance is shut down or terminated, that storage goes away. That's why customers only use it for temporary data or checkpointing, so that if there's an error in the middle of their training job, they don't have to start all the way over. Another service that customers also use for the same type of storage use cases, checkpointing and temporary data, is EBS. EBS offers raw block-level storage options for customers where these volumes are able to be attached to multiple different EC2 instances. This makes it easier for customers to share the same data across different instances within a cluster. We also have Amazon S3, which is an object storage system that is highly scalable. This is where we see customers storing their largest data sets with petabytes of data. For customers that are looking to get the best performance from our storage services, they use what Divish mentioned earlier, which is FSX for Lustre. This is a fully managed file system that has high performance, and as mentioned last week, we announced that it now supports EFA and NVIDIA GPU Direct Storage. This makes storage faster to your accelerator by directly connecting your data storage to the accelerator memory. This enables customers to get up to 1.2 terabytes per second of throughput from their file storage system to their accelerator. So moving on, we've talked about the different components in both the accelerator and switching layer. Now we'll talk about the components within the host layer.
Yeah, so as we mentioned earlier, the host layer has the CPUs that actually host the instance that you launch an SSH into. The host layer also has our Nitro cards, which ensure that your compute environment is kept secure. But let's talk a little bit more about why security is so important in generative AI. A typical Gen AI app is an interesting multi-party interaction. You have the end user that's interacting with the model, submitting prompts and receiving completions. And they may be sharing personal data, and they need to have the assurance that that channel is confidential. You have the model provider that's probably invested significantly in developing the model and needs to ensure that their IP or the model weights are kept secure at all times. Oftentimes, there may be a third party that actually took an off-the-shelf model and fine-tuned it on a particular proprietary data set. In that case, you need to ensure that your data set and your fine-tuned weights are kept secure as well. And then finally, there's Amazon as the infrastructure provider, which provides the underlying compute to make the application possible. So how do we keep all of this secure? I'll talk about 3 capabilities and then quickly through one use case. One of the capabilities is what we call no operator access, or zero operator access, which is a fundamental design principle around which we build every component of the AWS Nitro system. From the 3 components are up there: the Nitro cards, the Nitro security chip, and the Nitro hypervisor. What this means is that there's no mechanism for any operator at Amazon to SSH or access your instance. So this is how we keep the compute layer secure. We also offer services like VPC encryption. We talked about EFA earlier. Actually, all EFA traffic is encrypted by default, meaning that information going between your instances is kept encrypted as well. You can also encrypt your data at rest using services like Amazon KMS. And so we offer a range of building blocks to ensure that every aspect of the signal chain, from your end user to the data, to the network and the compute, can be kept secure. Let's talk quickly through one use case where you want to provide additional assurance to your end user that their application is running within a trusted environment. You can implement this using Nitro TPM, which can measure the code that you deploy. And maybe you deploy hermetic code, meaning there's no way to interact or SSH into the instance. And Nitro TPM can measure the code and compare it to known good measurements of the code, so that if any line of the code or any character in the code base is changed, it'll change the output of that hash function, which could be shared with the third party, for example, notifying the third party that that code has been altered. Using this, you can give your customers even greater assurance that their application is always running in a trusted environment. And so this is one use case with one example of several that you can use to offer additional security to your customers. So now that we've talked about security and some of our other capabilities in general, let's dive into our EC2 instance portfolio and the different offerings we have there for different use cases.
We've taken the different components that we just discussed within our compute architecture and packaged them in different ways to offer customers a broad portfolio of different instance types that they can choose from to make sure that for their specific workload, they get the best overall performance and cost. We have 2 generic groupings that we use for these different types of instances. One are the instances that are powered by custom AI accelerators. As mentioned, we have accelerators that are AWS built, so Inferentia and Trainium, as well as AI accelerators from Intel and Qualcomm. The second group is the GPU-powered instances. These instances feature a broad range of different NVIDIA GPUs that customers can choose from in order to make sure that they have the right amount of performance at the lowest cost. So now we'll talk about different instance lines that we have within our hardware accelerated portfolio, starting with the G instances. The G instances are powered by GPUs that NVIDIA optimizes for both compute and graphics workloads. And they range from entry-level developer type GPUs all the way to NVIDIA's highest performing GPUs for compute and graphics. These instances are great for customers that are looking to deploy single GPU workloads. We have 2 different instance types within our current generation of G instances, starting with the G6 instances. These instances are powered by NVIDIA L4 GPUs, which come with 24 gigabytes of GPU memory. So using the math calculation that Devish used before, that means you can deploy LLMs with up to about 12 billion parameters or smaller diffusion-based generative AI models. For customers that are looking to deploy even bigger model types, we have the G6E instances, which feature NVIDIA L40S GPUs. These GPUs have twice the amount of GPU memory, so 48 gigs per GPU. allowing customers to double the size of the models that they're deploying. In order to help customers take advantage of the extra GPU memory and the extra compute power of the L40S GPUs, we also doubled the amount of instance memory on G6E, giving customers up to 1.5 terabytes of instance memory, as well as quadrupling the amount of network bandwidth, giving customers up to 400 gigabits per second of bandwidth. Both the G6 and G6E instances come in 8 different sizes with 1, 4, or 8 GPUs paired with varying amounts of vCPU, memory, network bandwidth, local storage. This allows customers to make sure that they're getting exactly the amount of resources they need and no more, allowing them to better cost optimize as they're looking to deploy their models into production. So next we'll talk about the other GPU family that we offer.
Yeah, so our P-series instances are purpose-built for large-scale distributed training workloads, but they can be quite useful for LLM inference as well. I'll talk about 3 capabilities of our P-series instances. The first is NVLink, which is a highly performant chip-to-chip interconnect that exists in our P3, P4, and P5 instances. On P5, for example, any 2 GPUs can talk to each other at 900 gigabytes per second at microsecond-level latency. This means you can optimize your collective comms within an instance, as we spoke about earlier. The second capability is EFA networking. And these instances feature the highest networking, as we mentioned, actually of any instances across the entire EC2 portfolio, at 3,200 gigabits per second of EFA networking. Yesterday, we announced P5EN, which further optimized our EFA networking for better NIC utilization and lower NIC latency, further improving distributed training performance. And finally, let's talk about the GPUs themselves. These instances feature the most powerful GPUs from NVIDIA. On P5, we feature Hopper GPUs with H100 and H200 GPUs. And these GPUs each have up to 140 gigabytes of memory, meaning that you get over a terabyte of GPU memory within an instance. So coming back to Llama 405B, that can actually comfortably fit within a P5EN instance for inference, for example. We're also partnering closely with NVIDIA on their Blackwell GPUs, and we're really excited about GB200, for example. GB200 is establishing somewhat of a new paradigm in accelerated compute, where customers can access up to 72 GPUs within one NVLink domain. That's compared to 8 on P4 and P5. This means that customers can access over 13 terabytes of GPU memory and 180 petaflops of FP16 compute within one compute domain to train and inference multi-trillion parameter models right out of the box. I'll cover 2 other aspects of GB200. The first is the superchip architecture from NVIDIA, where the CPUs and the GPUs are co-packaged within one compute module. And this provides truly heterogeneous compute for the next generation of machine learning workloads that can use CPU cores and GPU cores in parallel. The other aspect is that Blackwell will actually be our first liquid-cooled platform at Amazon, and we're very focused on scaling our liquid cooling infrastructure to deploy Blackwell globally. Liquid cooling enables us to deliver even higher performance per GPU, meaning that your workloads get higher performance. So that covers our GPU instances, but what about our custom silicon instances?
So we'll start by talking about our INF series, which are powered by our AWS Inferentia custom ML chips. We first launched INF1 right here at reInvent in 2019, and then we followed that with INF2. With INF2, we improved the design of not only the Inferentia chip, but also the instance type as a whole, which enabled customers to get 4 times more throughput and 10 times lower latency than INF1. INF2 offers customers the highest performance at lowest cost for deploying their Gen AI models. Similarly to the G instances, INF2 comes with multiple different instance sizes that come with 1, 6, or 12 accelerators so that customers can get the right amount of resources for their workloads. The Inferentia 2 chips come with 32 gigabytes of memory per accelerator, but they are also linked together using Neuron Link, which means that customers can get access to 10 terabytes per second of aggregated memory bandwidth. This enables customers to deploy even larger models on a single instance, where customers are now able to deploy models with up to 175 billion parameters on a single Inference 2 instance. So now let's move on to the training side.
Yeah, so our Trainium instances, as the name suggests, purpose-built for training workloads. We were really excited to announce the GA of Trainium 2 yesterday, which will offer the highest performance across our portfolio for training at up to 40% better price performance. Each Trainium 2 instance has 16 accelerators connected over Neuron Link with, again, over a terabyte of accelerator memory within the instance. These instances also feature 3200 gigabits per second of EFAB3 for optimal scale-out. We were also really excited to announce the preview of Trainium 2 Ultra servers, which connect up to 64 Trainium accelerators within one compute domain. This offers you with over 5 terabytes of accelerator memory, again, to train and inference the biggest models in the industry. OK, so we've spoken about our EC2 capabilities and our EC2 instance portfolio. Let's now talk about the generative AI stack and how we're making this compute more usable for our customers.
So at the bottom layer of our generative AI tech stack, we have the infrastructure layer, which we just talked extensively about. Right above that, we have managed services that customers can use for training and deploying their models, as well as orchestration systems that they can use to manage their infrastructure. So that's where we have services like Amazon SageMaker and Amazon EKS. The next layer above that is where we offer tools that customers can use to obfuscate the infrastructure layer. So we offer things like Amazon Bedrock, which is a serverless service that enables customers to access industry-leading foundational models and deploy Gen AI models into production. The highest level of the tech stack are applications that are already built with foundational generative AI models integrated into them. And so that's where you'll see things like our AI shopping assistant mentioned earlier, Rufus, as well as Amazon Q, which is a generative AI assistant that enhances business productivity, as well as creating a more intelligent and capable Alexa. So we're going to look into 2 of these specific services within the tech stack, starting with SageMaker. SageMaker offers customers end-to-end managed services to help their data scientists and their ML engineers prepare data for AI training, train their models, and deploy them into production. Amazon SageMaker Studio specifically helps customers with the development of their models. It provides customers with scalable tools for data cleansing, data enrichment, and error detection prior to starting their training jobs. Additionally, this morning, we also announced in preview Amazon SageMaker United Studio, which is the next generation of SageMaker Studio that helps customers collaborate even more across their ML scientists, allowing them to build even faster. Additionally, we announced in general availability Amazon SageMaker Data Lakehouse, which is enabling customers to reduce data silos, allowing customers to unify their data across services such as Amazon S3 as well as Amazon Redshift. Another service that Amazon SageMaker offers is SageMaker for Training. This offers managed services for customers to train and fine-tune their ML models, allowing them to easier manage and track their training jobs, debug any errors within their training jobs, and monitor the utilization of their infrastructure. SageMaker Training will automatically scale your training job from 1 GPU to hundreds of GPU to ensure that your training costs are as optimized as possible. Additionally, with distributed training libraries that SageMaker offers, customers can use them to automatically split their models and their training datasets across GPUs, allowing them to speed up their training jobs by up to 40%. So next, we'll talk about Bedrock.
Yeah, so for a lot of our customers, there isn't a lot of value in pre-training a model from scratch. Off-the-shelf options like Claude or Llama are highly performant, and so it makes a lot more sense to just take one of these models, fine-tune it on a particular data set, and then deploy it quickly to production. We launched Amazon Bedrock last year to simplify every aspect of this experience with a dedicated set of APIs. Bedrock gives you a range of models to choose from providers like AI21, Anthropic, Cohere, and Meta. And you can take one of these models and get up and running within a few minutes. With Bedrock, you can also get access to newer techniques in inference without having to implement it from scratch. One example is retrieval augmented generation, where you take your user's prompt and you actually supplement it with additional context before passing it to the model for inference. This can help your model give more meaningful and relevant responses because it has additional context. Rather than having to piece together all of the different components into this pipeline, knowledge bases from Bedrock gives you an end-to-end solution to get this up and running quickly. OK, so we've talked quite a bit about the industries and use cases, the capabilities that we offer in EC2 and a generative AI stack. Let's now learn how our customers are putting this to use. And Kirmani, it'd be great to learn a bit more about the work that your team is doing at Meta.
Absolutely. And thank you, Samantha and Dwij, for that amazing overview of EC2 capabilities. We use EC2 every day, but it was really amazing to see everything come together in one deck. I'm going to be talking about how we put AWS to use for Meta. And hi, everyone. My name is Kirmani, and I'm sorry to be standing in the way of your dinner last 20 minutes. I'm honored to be presenting here on behalf of the Variables AI team at Meta. And the story that I wanted to tell today is really about how AWS and Meta partnered to solve one of the most technically complex problems and went 0 to 1 on creating the world's best variable AI device. Before I talk about the technology, let me just kind of give you a preview of the product. Let me introduce to you Ray-Ban Meta. It is the best pair of smart glasses that you can buy in market today, period. And even without all the smart features, first and foremost, Meta and Luxottica partnered to design a cool-looking pair of glasses. Beyond looking cool, these glasses can do a bunch of capabilities that you cannot do with your phone. Let's take a quick look at that.
Listen to music without muting the world around you. Live stream your creations from your POV. Take calls without interrupting your flow. Capture your unique perspective in an instant, straight from your glasses. The next generation of smart glasses by Ray-Ban and Meta.
So you can see that these glasses allow you to be present in the moment, enjoying and fully immersed in what you're doing, and let the glasses do the hard work. As amazing as the features that I showed you are, the most exciting thing you can do with your glasses today is use Meta AI on them. When you talk to Meta AI using your glasses, the glasses can actually see what you see and hear what you hear and translate and analyze everything that are in front of you to get you the best answer to your questions in the moment, in the shortest possible time. Let's take a quick peek at what that looks like in real life.
Hey, Meta.
Hey, Meta. Hey, Meta. Look at this building and tell me about it.
Look and translate this.
Look at this and tell us what to make.
Look and tell me what kind of butterfly that is.
That appears to be a painted lady.
These Meta AI glasses are one of the best use cases of AI for our users. In fact, these glasses have become so popular that they're outselling regular Ray-Bans in many stores. We launched a bunch of AI features when we first introduced these glasses last year at 2023 Connect. But since then, we have been launching a new set of features every couple of months. For example, this Connect, we launched visual reminders, which allows you to remember visual information, such as where you parked your car and where did you last lose your keys. We've also enabled these glasses to act on your behalf. For example, they can scan a phone number and call it for you, and they can scan QR codes. This is just the very beginning of a long and exciting roadmap we have for AI in 2025 and beyond. So how exactly did we get here? And that's the story I wanted to actually tell. Not only did we get there, but we got there really fast. As some of you might know, moving fast is one of the core company values at Meta, but how fast are we really talking about here? To give you an idea, I'll share an anecdote. It was a couple of months before the launch of Ray-Ban Meta, and our CEO, Mark, called the vice president of augmented reality while he was driving down a highway with his kids on a Saturday. And he goes, hey, those glasses that you're shipping in a couple of months, can we put Meta AI in them and ship them fast so that we can see if it's a good idea or not? And this is literally a couple of months before the launch. And since that phone call, the entire team rallied to put Meta AI and smart glasses, and the rest has been history. Let me dive now into how did we exactly build the Meta AI for these smart glasses. It all starts with Llama. Llama, I'm sure, as you all know, is the leading open source model family, and it's quite the revolution in open source AI innovation. We've launched 3 generations of these models in the last 18 months, and every single generation is way better than the last one. It's been downloaded 350 million times to date, 20 million in the last month alone, and it's really turbocharging the cloud and businesses that it touches. We're seeing 10x growth year over year. And before I dive into any of the technical details, let me kind of quickly remind you what Llama actually looks like. Llama, just like other large language models, understands text and generates text. It's trained on about 15 trillion tokens of text across 24,000 GPUs. That's our flagship model. And at about 400 teraflops per GPU, that is a lot of compute that went into training this model. As capable as this model is and can perform a lot of different tasks, it does not understand images and audio. It cannot see what you see and hear what you hear. And that's what was lacking when we started experimenting with Llama for smart glasses. We needed to make it understand what our users are seeing, and we needed to make it multimodal, and we needed to make it multimodal really fast. And this is what might be counterintuitive, is that training a multimodal large language model might seem like a task that we would need to do from scratch, but a key insight enables us to move quite fast here. And that is that you can use another AI model, it's a vision model, called a vision encoder, an image encoder, to take the input image and convert it into a set of tokens that the base Llama can actually natively understand. We still have to train it on quite a bit of data to help it understand the visual context and knowledge it needs to answer all your visual queries and answer them successfully. But that cost is on just a small subset compared to the large number of tokens we trained the base Llama on. The challenge we interestingly ran into when we started experimenting with LLMs is that there were about a dozen choices on how to build one. And all of them seemed like really good choices, but we weren't sure which one would work best for our use case. And the challenge comes from the fact that smart glasses input is inherently a very, very noisy input. It's very different from using generative AI on your phone, on your desktop, because you're typing into a keypad. With smart glasses, there's a lot of noise, there's a lot of audio, and you need to deconvolve the signal from the noise. So we needed to build the multimodal model for smart glasses, and we needed to build it really fast. And this is where really AWS came into play. AWS was critical in turning our explorations into insights. When we were in the market for cloud compute, there were 3 important things, some of which Sam and Duj already alluded to, which is the ability to fast prototype. And this is where the bare metal software platform from Amazon was really critical in taking GitHub and Hugging Face repositories and turn them into large-scale trainings for experimentation. We also needed the platform to be highly reliable and cost-effective because we needed to run multiple parallel experiments at scale, and that's where AWS hit the nail on all 3 for us. Let's now really talk about, step by step, how did we build the multimodal model, and where did AWS play a critical role? The multimodal recipe for us was 3 parts. We prototyped and experimented to pick the right architecture. Then we needed to train a base model that was good enough to iterate on and scale. And the third and the most important challenge was scaling it to a much larger size so that we could get the accuracy we needed. Step 1. Like I mentioned, there were about a dozen good choices of what would make a good multimodal LLM. But they fell really in 2 architecture families, the cross-attention style architectures such as Google Flamingo, or decoder-only architectures such as Lava, which are another popular or open source alternate. We ran hundreds of ablations in parallel over the duration of a couple of weeks, and each one taught us about what worked and what didn't, and provided insights on the compute quality trade-offs that we would need to build the model. And this is, again, where AWS's software stack really, really helped us move fast. In the end, we actually converged the learnings into our own architecture called Animal, which we open sourced recently. Animal, or any modality augmented language model, quite the name, is the best egocentric multimodal model that you can find out there. Once we picked the right architecture, the next one was to train a competent base model. And that looks pretty familiar to what Duj and Samantha already talked about. The first step is to actually train the image vision model itself. This model, although it's smaller, it still needs to see billions of images. And so we used AWS to scale up the training quite fast and train a model that would bring the images into the same representation space that the llama could understand. Once we had trained the model, the next step was to connect it to the base llama, and that happens through a pre-training process called projection. In this particular step, we train the llama and the vision encoder together to produce the most accurate descriptions of an input image. We follow a training paradigm called caption first and ask questions later. This takes about 1 billion images and runs at a very large scale as well. And finally, we fine-tune the model on a large variety of tasks because our customers could use it pretty much for anything. And this is done through a process called instruction tuning. We trained our model on about 12 tasks that are suited for smart glasses use cases, ranging from providing inspiration and recommendations to writing creative editing based on what you see, answering visual questions, obviously, captioning the images, and also extended the capabilities from vision to audio and motion signals. One of the interesting things we found about multimodal LLMs is that a composition of modalities often yields the most surprising results, as you can see in one of the examples listed here. Another key insight I wanted to offer is that these models actually learn to focus on what the query is, regardless of what the input image might look like. For example, for the same input image, if you ask it what the name of the hotel is, your attention goes to the right pixels there. If you ask it for the weather, it decides to look up. If you ask for the right dress, it would focus on the right pixels. These insights also allowed us to focus on quality and move fast. Now for the most important step. It is to scale the model. We had picked the right architecture, and we had trained a good base model. It was time to scale it. How does scaling look like? When we first trained our model, it was about 5 billion parameters and about 1 million image text pairs. And we scaled that up to about 80 billion parameters and 3 billion image text pairs in less than a year. That's quite a bit of scaling. And that's still not good enough for us. Because to hit the accuracy we need to scale up the model to another 100 billion parameters as well. And this is our next checkpoint that we are training. As you can see, that the amount of flops required to train also jumped about 2 orders of magnitude to get to the accuracy number we want. Hitting that many flops within the time window that we have to ship products is a very, very compute-intensive operation. When we first trained the model, it was on just 4 A100 instances, just 4. We're currently training on hundreds and thousands of H100 instances, and soon we'll be transitioning to H200s and GB200s as well. Compute being one aspect of scaling, storage was another big one. These multimodal data sets tend to be hundreds of times larger than their text counterparts. Our storage needs grew from about 100 terabytes when we started training to hundreds of petabytes within this span of 1 year. New experimental file systems had to be developed in order to support the scale. But it really comes down to the 3 challenges that Duj and Samantha alluded to. It's reliability, scalability, and efficiency. And these challenges really intricately influence the 3 quantities that are at the heart of every AI training: compute, comms, and memory. And every AI engineer that has worked training GPUs will tell you that compute is king. Because memory is a hard limit, you don't get more than what the hardware offers. Comms needs a ton of effort to get right. Your workload needs to be optimized a lot. But really, compute is king. So in order to hit the right amount of flops to train our model, we need our GPUs to always be computing. GPUs, as we know, are massively parallel devices. They're optimized for throughput. And to utilize them fully, you have to give them enough work. And this also plays an important role in efficiency. But before we get to efficiency, one of the first bottlenecks we needed to solve, and this is where it was really critical to partner with the AWS team, was on reliability. When we first set up our cluster, we ran into a number of setup issues regarding file system failures, faulty nodes, and mismatched software dependencies, just the setup cost. But the AWS team, along with our Meta high-performance computing team, was really meticulous in looking at every issue we ever had and resolving it within a matter of few hours on many instances. We went from actually failing on all of our nodes that are about 2025 for the first month of our training. And I remember distinctly the day when we transitioned our home file system to Lustre. And then voila, we were running hundreds of nodes for weeks at a time without any failures. And our cluster utilization shot up within a couple of days to about 20 times more. So that was, thank you so much, the AWS team for pulling that off. Once we had the reliability that we needed to scale the training. And the first thing to do is to really optimize your workloads. And this is done through basically parallelization. There are different types of parallelization, some of which was already alluded to in the last talk. But the two main ones are about data and model. There is about a dozen of parallelization techniques. We threw the whole kitchen sink at our training. And we got about a 16x speed up, combining FSDP, which is the most popular form of sharding, along with tensor and model parallelism and the quantization, that optimized quantization for our model training. But again, everyone who has dealt with large-scale training will tell you that software will only get you so far. One of the main bottlenecks beyond a certain point is really the hardware. Once you scale up your workloads enough, you start to tail off on the efficiency once you've hit the max number of GPUs. Throwing more GPUs isn't going to help you scale the training. And this is where better hardware comes into play. Now, we were already using H100s, which is the best that's out there. So what else could actually get better for us? And this is AWS delivered an interesting surprise for us. When we looked at our cloud benchmarks and compared it to AWS, we saw about a 2x increase that came for free without actually optimizing anything about our workload. And that was because AWS uses a 900 gigabits per second interconnect compared to 600 on other benchmarks. We're almost at time, and I wanted to actually close with some of the future needs for multimodal AI and pass it back to Duj and Samantha for closing. The three main challenges that we look ahead in 2025 is to scale our models, and this goes very well with the roadmap that the AWS team also presented. We need to train about trillion parameter models in order to really fully exploit the multimodal capabilities of these models. We also need to support very long context length for use cases like videos and session-based experiences. And most importantly, as we sell more devices and these users engage and retain with the Meta AI features, we'll need to scale our inference to support the user growth. And the three key levers are the same ones that got us here. It's a full circle in many ways. We still need to do fast prototyping and experimentation that will allow us to pick the best architecture for the trillion parameter model. And in order to enable that, we need to scale our compute, moving from H100s to GB200s, and the exciting potential they offer is going to be critical. And faster inference is going to reduce those latencies, drive more engagement around the users, and provides us with an opportunity to learn from user feedback. And with that, I'd love to acknowledge the AWS team and everyone here, the Meta high-performance computing team for their effort, as well as my home team that made all of this work possible. So thank you so much for your time, and back to you.
Thank you.
Yeah, we'll wrap this up real quick for you guys. We want to start by also thanking Kirmani and the Wearables AI team at Meta for sharing all those valuable insights into their workload. And we want to thank all of you guys for joining us tonight. We know it's late, and we appreciate you being here.
Yeah, we may not have time for questions, but we'll stick around in case you want to ask some questions after the talk. So thanks, everyone.